Hello there, this is an Algebra 2 video. It is Chapter 7, Section 7, and today we'll be continuing our study of exponential functions and logarithms, and specifically talking about base E and what we refer to as natural logarithms. So first and foremost, we got to tell you what the number E is. Like pi and square root of 2 and such, E is not a variable. We know what E is. E is approximately, it's an irrational number, which means that it has a decimal approximation that goes on forever. It never repeats itself, just like the number pi. But approximately, E can be approximated to be 2.71828. Most of the time we just go 2.718. And so just so that you know, a lot of times we use E with exponential functions, so we could have things like e to the x. But what I have on the board here shouldn't be too strange to you, because we've talked about exponential functions in the past, where we had 2 to the x power, 3 to the x power, and even to the negative power. So we know that when you have a positive x, e to the positive x, you have an exponential growth function indicated here by the blue. We also have this red line here to indicate that we also have inverse functions, and they're always mirror images of each other along this line. And so the inverse function of e to the x, you know that we've done 2 to the x, and we know that logarithms are the inverse functions to exponential functions. And so it's important that we know that there's also a logarithm that has a base e. Just like there's a logarithm with base 2 and base 10, there's a logarithm with base e. And when you have log base e of x, instead of writing log base e, what you're going to see happening is ln x. And ln x is actually stands for natural logarithm. The n is for natural, the l is for logarithm. And if you're wondering why it's backwards, that's because it's Latin. And in Latin languages, unlike English, where you would say something like red car, in other words, you describe the car before you actually say the noun, so the adjective goes before the noun. Red car. In Spanish, it'd be backwards. You would say carro rojo. You would say the noun first and then describe it afterwards. And so we're saying logarithm natural. So we say the logarithm and then we describe it afterwards. So it's ln. But yet when we say it in English, we always say natural log. So it's just kind of confusing, but just a little bit of tidbit of information for you there. But it's ln x. And so over here, what I have here is the exponential decay function. When you have a negative exponent here, it's going to be decay. But likewise, you have the inverse function, which would be negative ln x. Now, we know that we can't have ln. You can't take the log of a negative number, and of any log, including the natural log. So this is, I just want to be very clear that the negative is in front of the ln, not after the ln. In case any of you are going to question that, because I've told you in the past that you can't have the log of a negative number. The negative is in front of the log, not on the other side. So just what these look like. I'm not going to be graphing functions today, but I wanted you to see the similarities between e to the x and 2 to the x and all the other exponentials. So the first thing we want to do is basically get started with all of the things that we've already done with other exponential functions, with other bases. We're just going to now include the base e as well. So the first thing we want to do is write the exponential equation in logarithmic form. So you will remember that I had that little diagram for you. So what we want here is log base e of 8 equals x, because we said that we want that little diagram to happen. So we have e to the x power equals 8. So e to the x equals 8. So to put it in a log, you would write it this way. But instead of writing log base e, we're going to get rid of the log base e and start writing ln, which is the same thing as log base e of 8 equals x. So this is my logarithmic form. Same is true over here. We're going to say log base e of x equals 5, because e to the 5th power equals x. And then to write it in, instead of log base e, we're going to put ln x equals 5. And so those are my two solutions for my first part. And now you can try do it yourself, number 1 right here below. And then we will move on to the reverse of that. So now we want to take logarithmic and write it in exponential form. So again, the thing to remember here is that when you see the ln, it's log base e. So we want to say, you could even put log base e if you'd like to kind of help you see that it's e to the 0.7741 power, and that's approximately equal to x. E to the 0.7741 power, approximately equal to x. That would be my solution for that one. And same thing here, we can write log base e, so we're going to go e to the x power equals 10. And we'll take it from logarithmic form to exponential form, just like that. So now you can try to do yourself number 2. And then we're going to go, also the same thing applies to natural logarithms that applies to regular logarithms as far as condensing and expanding. When you write expressions as a single logarithm and when you expand it, all those properties still ring true. When you put a number in front of the log, it becomes the power. So you can have, in this case, ln 10 to the third power minus ln 8. Of course, when you have a subtraction, that turns it into a division problem. So now we're going to have ln of 10 to the third divided by 8. And then we know that 10 to the third power is 1,000 divided by 8 actually ends up being 125. So 125 could be written as 5 to the third power. And the 3 can come out in front, and the final answer could be 3 ln 5. 3 ln 5 would be our final answer there. And then we have over here, same thing, we have ln 40, and then the 2 here can become the exponent, and that's going to give you ln of 1/2 squared plus ln x. So when you take the 1/2 and you square it, that's actually going to become ln 1/4, because 1 squared is 1 and 2 squared is 4. And you still have ln 40, and you still have ln x. So now these are all addition, and so we know that when we have addition like that, we can actually multiply. So we're going to say ln of 40 times 1/4 times x, and since 4 goes into 40 10 times, you're going to get ln of 10x, and then that's all you can do with that little guy, because they want a single logarithm, so you don't want to actually split this into 2, so you want to leave it like that. So that will be your answer for part B. So now you can try doing the same thing for this little guy, and then we're going to go on to solving exponentials with base e. So it says solve 4 times e to the negative 2x minus 5 equals 3. It says round to the nearest 10,000. But you can solve exponential equations that have a base e just like you could any other type of exponential. So we want to first and foremost move the 5 over to the other side. So we get 4e to the negative 2x equals, if we add the 5 to the other side, we're going to get 8. Then we want to get rid of the 4 here, so we're going to divide by 4. So e to the negative 2x equals 8 divided by 4, which is 2. And now is where we can actually incorporate the use of logs. So you recall that you can take the log of both sides. So I will say ln of e to the negative 2x equals ln 2, because the inverse of an exponential is a logarithm, so that's what we're doing that. The exponent here then goes in front according to our properties, so you get negative 2x times ln e equals ln 2. And ln e is an interesting situation. Ln e is actually 1. And if you don't know why, I can tell you over here that that's log base e of itself. Because remember that log base e is the same thing as ln. So when you have ln e, it's log base e of e. So the question that you're asking there is e to what power is itself? Well, this would have to be a 1. So log base e of E is 1, therefore ln E is 1. So anytime you have ln E, you're going to get 1. So basically, 1 times negative 2x is just negative 2x equals ln 2. And so finally we divide by negative 2. And so the exact answer is x equals negative ln 2 divided by 2. But it did tell us to round to the nearest 10,000. So we're going to go ahead and put that into our calculator. And we're going to go negative ln 2, so we use my ln button, 2, and then divide that by 2. And that's going to be approximately negative 0.3466. All right, 3466. Now I want to tell you that you are better off, instead of trying to put all of that into the calculator at one time, you are better off figuring out the natural log of 2 and then hitting enter, so getting a solution, and then dividing that answer by 2 afterwards. When you try to put all the keystrokes in there at one time, most students make mistakes because they don't put the parentheses in the right spots. I'm not saying that you can't do it, I'm just saying that if you didn't get the right answer, it's probably because you didn't enter into the calculator correctly. All right, so now we're going to let you do this example, and then we are going to go on to equations and inequalities that have logs in them. So in the last example, we solved an equation that had an exponential with a log, but now we want to solve a log with an exponential. So again, there are some different approaches to how people like to do this, but to each his own. Yes, I think the first thing that I would do in part A is, some people can try to make the 3 be the exponent over here, but since I know that 3 goes evenly into 24, probably the best thing that I can do is to divide both sides by 3, and then that'll give me ln 4x equals 8. And then again, this is log base E, so if you want to write that instead, if that makes it easier for you, then we can use our exponential form, which means this is e to the 8 equal to 4x. And so when we divide by 4, the exact answer is x equals e to the 8 over 4. And again, they do want us to round to the nearest 10,000. So we're going to go e, which is above the ln button, to the 8th power. Gives me a really large number. I divide that number by 4, and we get approximately 745.2395. Staying true to the 10,000th place there, we're going to get 745.2395. Alrighty. In the case of the inequality, you have to remember that when you do the exponential thing, we're going to have to use our property of equality for exponential functions. So basically, in this case, we already have, there's nothing to divide by, but we have log base E of x minus 8 to the 4th less than 4. In this case, I actually think, well, I think we have an easier way of doing this. We're going to go e, so we're going to get e to the 4th power x minus 8 to the 4th power, like that. All right? X minus 8 to the 4th power is less than e to the 4th. Yes. Okay. So now what we're seeing is that they both have the same exponent there. And because they both have the same exponent, the only way for them to be equal is for x minus 8 to be equal to e. So now we can say that x minus 8 has to be less than e, because if it wasn't, then the fact that they have the same exponent, there, that wouldn't work if they weren't the same. So now we're just going to add 8, and then the answer is x is less than e plus 8. That's the exact answer, but we can figure out what e plus 8 is by using the calculator. E to the 1 power plus 8, and we get approximately 10.7183. All right, and that is how you do that. So now we're going to let you do this do-it-yourself question, and then we have one more example, probably the most fun of them all, if I can get my board to cooperate, and that is continuously compounded interest. So we have a formula for that. It's I like to refer to it as PERT. I'm not sure if PERT shampoo is popular anymore, but it was when I was growing up. PERT Plus was the first shampoo that had 2-in-1 shampoo and conditioner in the same bottle. But the reason why I bring that up is because the letters here is exactly the way you spell PERT. Has nothing to do with shampoo, but it kind of helps you remember that it's the PERT formula. So A is the amount in the account after T years. P is the principal or initial amount that's invested in the account. E, of course, is not a variable. It's a number, 2.718 approximately. R is the annual interest rate, and then T is the time in years. So with this formula, you can actually, it replaces the simple interest formula, which is the 1 plus R over N to the NT formula that we had in the previous sections. So here we have, we're going to use that formula in this example. It says when Angelina was born, her grandparents deposited $3,000 into a college savings account that was paying 4% interest compounded continuously. So in part A, it says, assuming that there are no deposits or withdrawals from the account, what will the balance be after 10 years? It's a really straightforward problem. We're going to, what will the balance be after 10 years? They want to know what A is going to be. So our job is going to be to solve for the A in the equation earlier. So we don't know what A is. But we know that it's according to this, the principal amount is the amount that was initially invested, which is at $3,000. And then E, and then the annual interest rate, 4%. So 4% means 0.04. So we're going to put 0.04 for R, and then T is 10. Okay, because it's after 10 years. So it's a really straightforward problem. We just want to figure out what this is going to be. Now, what I want you to be careful about is don't take 3,000 times E. Okay, what you want to do first is you want to take 0.04 times 10, which is only going to move the decimal, one place over. So you're going to now have 3,000 E to the 0.4. And so again, the thing that you should do first is plug in the E to the 0.4 power first in your calculator. So I'm going to do second and ln, so that brings up the E function. And then I type in 0.4, close parentheses, and I get 1.4918. I'm not going to do anything with that. I'm just going to automatically go times. So I'm going to take that amount, times it by 3,000, and I'm going to get approximately here $4,475.47. So after 10 years, she hasn't really made that much, roughly a little bit under $1,500 that the account has grown. And so now she has $4,475. It's not going to go very far this day and age as far as college tuition goes. But nonetheless, we've answered the question. Part B, it says, how long will it take the balance to reach at least 10 grand? So now we want the amount, A, to equal 10 grand. So this time we're going to say 10 grand equals the initial times E, same interest rate, but now we don't know what T is. It says how long. How long question means what is T? We're solving for T now. So, and it also says at least 10,000. So where we have this equal sign here, it might make more sense to write it like this. At least means that this amount needs to be greater than or equal to 10,000. At least 10,000 means greater than or equal to 10,000. So now we're going to solve by dividing by 3,000 first. And that's nice because it gets rid of a lot of the zeros. So E to the 0.04T. So on my calculator, we're going to go 10,000 divided by 3,000. and we're gonna get 3.333 repeating, so that's 10/3. So we're just gonna leave it as a fraction. We'll leave it at 10/3. We'll round it later. All right, and then we wanna take the log of both sides. So I'm gonna come over here, I don't have any space left, so I'm gonna go ln of e to the 0.04t is greater than or equal to ln of 10/3. And so here we know what's going to happen. This exponent is going to go in the front, and you're going to get 0.04t times ln e. But ln e, we said earlier, is going to cancel. And so we're just going to end up with 0.04t, and over here we're going to have ln of 10/3. And then we're going to divide by 0.04 on both sides. So t has to be larger than or equal to, we're going to go ln 10 divided by 3, close parentheses, I get an answer. Divide that answer by 0.04, and I get 30.099, so basically 30 years. Wow, that's a long time. So in about 30 years, she will have at least 10 grand. That's a long time to only have 10 grand. But we're not done because there's a part C. So over here it says, if her grandparents want Angelina to have 10,000 after 18 years, so we have 10,000 after 18 years, but it says how much would they need to invest? So we don't know what the initial amount is, so we're going to call that P. E, the interest rate is still the 4%, and the T is 18. So they've given us different information this time. We know that we want the account to be at 10 grand, but we don't want to wait 30 years. We want to only have to deal with 18 years, so that's T. The interest rate is still 4%, and we don't know what P is. So now what we're going to do is we're just going to divide by E. What is 0.04 times 18, you ask? Apparently 0.72. So we're going to divide by e to the 0.72 on both sides. That takes care of that. And P is going to equal 10 grand divided by e to the 0.72, which is actually 10,000 divided by e to the 0.72. We get that P is approximately 4,867.52. They have to invest at least $4,867.52 in order for her to have $10,000 at the end of 18 years. So they need to up their $3,000 deposit by another $1,900 or so to allow her to have 10 grand at the end of 18 years. So now you will try this little guide, and again there are A, B, and C. We have A and B on this screen, so you want to write that down, and then part C is right here. And once you have completed this do-it-yourself question, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.